All right, so we're going to take a look at Chapter 8 today and starting into really a lot of talking about bonding. And today's focus is mostly going to be on ionic bonding, some different things that kind of pertain specifically to ionic compounds. And then we're going to shift our focus towards the end a little bit towards covalent bonding as a lead into Lewis structures, which will be kind of our next lecture that we'll get a lot into. And so there's some things you'll probably be seeing in lab this week as well. So for ionic bonding, though, before we even really get too much into specifically ionic bonding, just to review kind of our major types of bonding that we talked about earlier this semester, which are going to be the ionic and covalent bonding that I've already mentioned. It's probably helpful to refresh ourselves about what's going on in these types of bonding and kind of what elements are going to be present in these types of bonding as well. And so ionic bonding typically is going to be between a nonmetal and a metal. It's one of the easy ways, if you're just looking at a chemical formula, to usually differentiate between ionic and covalent bonding. And what ends up happening is you have electrons that end up getting transferred from the metal to the nonmetal. Right? So your metal is going to get ionized, it's going to become a cation. The nonmetal is also going to get ionized and become an anion when it gains those electrons. It's effectively a redox reaction that occurs. And then you have two oppositely charged particles that will then attract each other. And that's where you're getting your bond formation from. In covalent bonding, one of your biggest differences is the fact that it's usually going to be between two nonmetals. At least for right now, it's kind of the only type of covalent bonding we've talked about. And electrons in covalent bonding are generally going to be shared. And so they're not going to be completely transferred from one element to another. Instead, since we have two nonmetals that, if we think about periodic trends that we talked about in our last lecture, if we have two nonmetals based on where they are in the periodic table, they're in that kind of upper right corner. Well, that upper right corner is where our more electronegative elements are. It's where elements that have higher ionization energies are. So these elements want electrons, and they don't want to give them up. And so as a result, when those you have two elements that are both nonmetals interacting with each other, we end up with shared electrons instead. It's kind of just what we see. And so we get that covalent bonding to occur. Now, things that are going to show up regardless of which bonding type we really talk about. Probably the biggest one that we're going to see kind of constantly throughout this chapter and really even beyond is something called the octet rule. And so where this idea of 8 kind of is, and we're going to see 8's really a magic number for electrons, where that magic number is going to come from is the fact that if you think back to the orbitals we've also been talking about, remember all of this stuff kind of all ties together. The S and the P block of orbitals that would comprise what we call our main groups of the periodic table. To fill all of our S and P orbitals on any given atom will take 8 electrons. And remember we said like filling orbital sets usually is really stable. And that's what basically this octet rule is mainly based off of. And so it takes 8 electrons to fill that S and P orbital shell. And so almost all main group elements, whether they're metals, nonmetals, doesn't matter. They almost all prefer to have these kind of noble gas electron configurations that result in your S and P orbital shells being full. And so most nonmetals, they prefer to do that by gaining electrons to become like a noble gas. But for a lot of metals, especially group 1 and 2 metals, it's easier to lose electrons and become like a noble gas. And now you basically have like the full shell for kind of the energy level beneath where you initially started. And in general, once you get your energy level to be full, so for instance, once you have kind of a noble gas electron configuration on something, it's really hard to break up. And so it's hard to either add another electron or take an electron off if you have that full energy level, basically if you have that full octet. And that's why when you talk about like ion charges and things like that, a lot of times ion charges for elements, what we end up seeing is that they prefer to have that noble gas configuration. Like all those charges, like the reason oxygen prefers that -2 charge we've talked about all semester long, prefers -2 because gaining those 2 electrons gives it that full S and P shell. That's the reason -2 is that preferred charge. Now, there are always going to be exceptions to the octet rule, and so I want to go over a couple of them that we're going to see. In terms of exceptions regarding ions, there's only a couple. Most of them are the really heavy P block elements. And so if I actually, let me go and show a periodic table here that I'm going to pull up. And so if we're looking at just a really generic periodic table here, the heavy P block elements are the ones like down here. So if we're looking like lead or bismuth or polonium, things like this, these are elements that do have possible charges to their ions, that don't match what you might normally expect based on the column that they're in. Right? For instance, carbon, silicon, germanium, most elements in this column usually like to be +4 a lot of the time. But when we get down to lead, lead's actually preferred charge is +2, although it can also be +4 in some compounds. And that's actually one of the reasons why earlier this semester when we were talking about different elements that you have to put Roman numerals for that aren't just transition metals, lead is one of the common ones that happens for, is because it can be +2 or +4. If we look at thallium, thallium's preferred charge is actually +1, even though everything else in its column is normally +3. And so these heavy p block elements, they do have kind of some of these strange behaviors compared to the normal trends of things. And one of the reasons for that is really, and it's, you might hear this term get thrown around, something called the relativistic effect. Basically, the s orbital electrons in those elements are really hard to pull off. And it's a result of something called the relativistic effect that we're not really going to go into too much of that in this class. Again, if those are things you're interested in, I would encourage you to take more physics, take more chemistry, because we do get into those topics, just not usually in general chemistry, unfortunately. Now, exceptions for our octet rule outside of ionic bonding, because really outside of those heavy p elements, for the main group elements in the S and P block, there really aren't any exceptions for the octet rule. Pretty much everything, the most stable ion is going to have an octet. That's the normal trend we're going to see for everything. Now, for covalent bonding, it does get a little bit different. For covalent bonding, it's possible that some atoms are going to be able to have more than 8 electrons, but not everything can do that, right? And so what's going to end up happening is that in order for something to have more than 8 electrons, it's going to have other orbitals to take those electrons on. So 8's the magic number because that's what it takes to fill s and p orbitals. So if we need to take more than 8 electrons, we need something that has other orbitals that can also be filled. And so our general requirement here is that we need to be the 3rd row or lower on the periodic table. And now we have d orbitals that can also take on more electrons as soon as we get to that 3rd energy level. And that comes really from quantum numbers again. Quantum numbers, if we're thinking about them, usually if you're in the 3rd energy level, n equals 3, L has the potential to equal 2 now, so we can have d orbitals. So if I go back to the periodic table here real quick for a second, elements like sulfur, even though we haven't got to anywhere where it's had to put electrons in d orbitals, just because it's in the 3rd row or the 3rd energy level, it technically has d orbitals. They're just empty. And so that's why something like sulfur or phosphorus or chlorine, these elements can pretty easily take more than 8 electrons around them in a lot of covalent compound structures. And so they have what we call these expanded octets. And it's because they have these extra orbitals to hold those extra electrons. Additionally, once we get to the 3rd row of the periodic table, not only do we have d orbitals, but the atoms are just big enough to be able to take those extra electrons. And so it's those two kind of effects combined make it so that pretty much any element in the 3rd row and lower, especially in the p block over here, is capable of having what we call these expanded octets in their covalent structures. And we'll be spending a lot of our next lecture taking a look at Lewis dot structures, where you'll get to see a lot more about kind of what those expanded octets look like and kind of reasoning through like when that's reasonable. Now, there's also the other side of things. We can have what we call incomplete octets. So these are elements that are okay having less than a normal octet when they make compounds. And this is a pretty short list. Mainly it's going to be hydrogen and helium, which are kind of the obvious ones. Mainly because if these are in the 1st row of the periodic table, that's only 2 elements across. There is no p orbital in that 1st energy level. There's only an s. So hydrogen and helium, instead of wanting 8 electrons, they only want 2. And we'll never see them with anything different. The other ones that are okay with having less than 8 electrons are actually going to be our group 13 or 3A metals. 3A elements. And again, showing which column that is, that's this column on the periodic table. So boron, aluminum, gallium, indium, thallium going down. This column on the periodic table is okay not having a full octet in covalent compounds. And we'll spend again some time in our next lecture looking a little bit more why this happens. But it's actually due to something called formal charge when we actually start looking at our Lewis dot structures. These elements, because they normally only have 3 valence electrons, to give them an octet actually makes them feel like they're an anion. And most of these elements usually would rather be a cation instead, so they end up not doing that. And so a lot of these elements in that group 13, like boron on down, usually okay having less than a full octet in their compounds. And again, we'll see kind of a little bit more with that later on as well. All right, now, next piece, what I really want to move into and kind of talk about for most of our time, or at least for the next little bit, is going to be taking a look at ionic bonding and really thinking about what happens in order to make ionic compounds, and talking about the energy that then is involved with this process, and also then some trends and patterns that we can look at trying to predict based on kind of what we know about different elements and how they would then make ionic compounds. So in general, formation of ionic bonds. We've kind of gone over this a little bit already, right? We said before, you typically have a nonmetal that is effectively removing electrons from a metal. So our metals end up being cations, nonmetals are anions. And if we think about why, again, we can go back to what we talked about in our last lecture. Trend-wise, metals usually have pretty low ionization energies, so it's really easy for them to lose electrons, whereas nonmetals usually have fairly negative electron affinities, meaning they give off a lot of energy if they can gain an electron, which means if it's pretty easy to take an electron off a metal, and we have nonmetals that really want electrons, that's why we get that transfer of electrons to make our ions. So kind of related to things we've talked about before. And then we have two oppositely charged particles at the end of that transition, and now we have two things that are very strongly attracted to one another because of that, and forms a very strong ionic bond. And when you hear people talk generally about ionic bonding or covalent bonding, in general, ionic bonding is a stronger attractive force because you have these fully charged ions attracting each other with opposite charges. And so we'll see some things with energies here in this today, kind of with ionic bonding and with covalent bonding, so kind of throughout the chapter. And we'll see be able to compare and look at some properties, and ionic bonds usually are stronger just inherently than covalent ones. All right, now the other thing that's going to end up happening to make ionic compounds and ionic solids in particular, we're not going to detail too much about what the structure of ionic solids looks like. That'll be one of the very first things we actually look at in 1212. But one of the things that we do want to kind of at least make a little bit of a note of now, when ionic compounds form solids, it's never just one cation and one anion. Even if it's like a sodium chloride where you have a +1 and a -1 charge, it'll never just be one of each. It's always going to be a ratio of all of the ions that are there. Because what happens when ionic compounds form is that you actually typically end up ionizing a lot of metals and nonmetals, and then you end up making this large-scale structure that's very organized and repetitive of all of your cations and anions arranging together to make this huge solid. And so when it comes to ionic compounds, we never have individual what we call molecules. Right? It's why earlier this semester, different terminology pieces, would hear the term like molecular compound would kind of get used interchangeably for like covalent compounds, because covalent compounds can have molecules. Ionic compounds typically don't. Ionic compounds, really, we always just give an empirical formula. That's just the ratio of the ions that are involved, because usually there's so many ions involved in making an ionic solid or just an ionic compound that we can't track all of the total number. And so we just give the lowest ratio because we know that is the ratio of the ions that's going to be there. Now, there is a terminology piece for this chapter, something called the lattice energy. That's going to be the energy that's associated with all of your cations and anions, basically arranging to form your ionic solids. So if you have a bunch of ions in the gas phase, combine them all to make an ionic solid, that energy change with that process is what we refer to as a lattice energy. And now, this is one thing I will point out, because depending on what textbook or what resource you look at, lattice energy is a little bit strange in terms of like the numbers that you'll often see for it. Sometimes, some books will refer to it as a positive value. Some books will always refer to them as a negative value. Me personally, for my classes, I always teach it as a negative value. That is the way it usually shows up on ACS exams as well. But various textbooks do outline it with different signs. If it shows it with a positive value, it's just defining it as the opposite direction. So if you have a book or a reference that you're looking at and it says the lattice energy of something is positive, they're just basically taking the viewpoint of how much energy does it take to take your ionic solid and break it apart to its ions. So it's just a directional kind of change in terms of like how it's being looked at or defined. So for me, like I said, I define lattice energy. It's the energy change when two ions in the gas phase combine to form the ionic solid, and that'll always be a negative value. So for that direction, always going to be a negative value. There are a lot of textbooks, like I said, out there that they will show this lattice energy as a positive value. It's not that they're necessarily wrong. It's just that they're defining lattice energy in the opposite direction. So it's something to be kind of just cognizant of and aware of when you're looking at things with lattice energy. Part of the other reason why I often talk about lattice energy always being negative, I think it makes more sense to think about it that way in terms of what we call a Born-Haber cycle. And that's really probably the biggest problem-based application we're going to see, or one of the two big problem types that we're going to encounter with a lot of this material or information for ionic compounds. And so what the Born-Haber cycle is, it's a cycle that takes the formation of some ionic solid from its just plain elements and their normal kind of standard states, however you'd find those elements, and it breaks down the formation of that ionic solid into all of the individual steps that have to occur in order for that process to happen and end up with that ionic solid. And it can be used for a variety of different things. You can determine lattice energy for the formation of ionic solids this way, although actually this is sometimes a way to find electron affinity, which can be tricky to measure for some different compounds also. And so it can be used to find a couple different things. But to give a general outline of a cycle, I'm going to show one here, and then I'm going to show just kind of an example problem that I'll work through that will hopefully kind of explain a little bit more of what's going on with this, what we call Born-Haber cycle or Born-Haber process. So what we see kind of in this image here, basically this step one, it's going to map through like what are the individual steps. So here it gives us an overall reaction. So our overall reactions, we have sodium solid plus 1/2 Cl2 is making NaCl as a solid. And something you will always see for the reactions in the Born-Haber cycles is that you are always going to make exactly 1 mole of product, which is why we actually have this fraction for a coefficient here. Right? Earlier this semester when we were talking about our coefficients, they always had to be whole numbers. This type of problem is pretty much the only time you might see these fractions for some of your coefficients. The reason for that is this equation right here. This is the reaction basically for that would correspond to what we call that enthalpy of formation for sodium chloride. That term like delta HF naught that we defined at the end of a couple chapters ago. And so because of that, that's why we're making exactly 1 mole of this product. So having a half here is actually okay. And in fact, having that half here is important because the stoichiometry of everything actually has to be kind of considered and thought about as we do this calculation. So what I'm going to take a look at here then, if this is our overall reaction, if we want to look at our individual steps, this is broken into 5 total steps. And so the first step that's shown here is sodium as a solid being basically what we call sublimed or sublimated into sodium as a gas. So it's going from the solid phase to the gas phase. And these red arrows and going up, these are all steps that we have to add energy to make those steps happen. So this is a positive change in energy because we're adding the energy to this process for it to occur. Like for anything to go from the solid to the gas phase, we always have to add energy. All right, second step in this process, we have chlorine gas. So it's Cl2, but we want it as just individual chlorine atoms. And some things to kind of think about. Your goal for all of these types of problems, if you have to map out like the individual steps in a Born-Haber cycle, is always for both the metal and the nonmetal, is if you're not as an individual atom in the gas phase first, get them to individual atoms in the gas phase. That's kind of the first step. And so we see for metals, it's almost always going to be a sublimation step, just going from a solid to a gas. For nonmetals, most of the ones that we look at, or they're going to show up in these problems, are usually diatomic. And if they're diatomic, so like Cl2, that means that we are going to have to break them apart into their individual atoms before we go about ionizing them. Because making like Na plus and Cl minus, that only happens if those atoms are already in the gas phase for us to be able to use those ionization energies or electron affinity values. All right, so those are our first 2 steps. Basically just getting both of these elements into their individual atoms in the gas phase. And then the next 2 steps are ionizing them. So for sodium, we're taking an electron off. So this energy right here is the ionization energy for sodium. So you see that's about 496 kilojoules per mole. It's a pretty big energy value, but it's positive. Now, chlorine. When we add an electron to chlorine, remember most of our electron affinities are actually negative. And so because chlorine's electron affinity is negative, adding the electron to it, its energy actually it's going to release energy for us in this process. And so we have an energy release in that step, and that's pretty common. The only time you wouldn't see a negative electron affinity is if you have some element that actually is going to be gaining 2 electrons, like if we had oxygen, in which case the second electron affinity is always positive. And that's just because like first electron affinity for all of our nonmetals is always negative, but for our nonmetals, the second electron affinity is positive because you now have an anion with a negative charge. So to add another negative charge to that, it's actually going to take energy no matter what we do. So that's just something to keep in mind. We don't usually see many examples of that in general chemistry, but it is possible in the future something like that could come up. Now, once we have chloride and Na+, so we have our ions in the gas phase, now we can take those 2 ions and put them together to make sodium chloride as a solid. That's kind of our last individual step of this overall cycle, and that's what we call our lattice energy step. And usually this is kind of the step that makes a lot of these reactions potentially exothermic. Usually the energy for our lattice energy is a very large negative value. So putting these 2 oppositely charged ions together to make a solid, it's extremely energetically favorable, releases a ton of energy, and so that's the one that we usually see as like this biggest negative value for these steps. Now, what ends up happening from all of this, as far as any calculation problems and things like that we'll see, is if we take the energy from all 5 of these different steps that we're given here, one of the things we saw in our energy chapter is that if we apply Hess's law, we basically have 5 different reactions that if we add all 5 of these reactions together, we get the overall reaction that we were kind of given at the start. And what that means, if I add all of these numbers together for all of my energies, they should give us a total energy then for the whole reaction. And so the next thing I'm actually going to do is look at an example problem. Basically, what kind of problems will be asked involving the Born-Haber cycle. And I'm going to show how to do this on kind of like the little side screen here as well to kind of help out. All right, sorry about the skip there. So we're going to take a look at this example where we're looking to calculate the energy change for the formation. And we were given delta HF naught, so really like the enthalpy of formation or heat of formation might be other ways you're hearing that referred to. But calculating the energy change or the enthalpy of formation of magnesium bromide as a solid from its elements in their standard states. And we see we have a whole boatload of information here, right? We have a bunch of different energies for all of these different reaction steps. We want to figure out how do we go about putting it all together. That's the big thing we want to try and do here. So to do all of that and kind of put all of the pieces together, I think usually the easiest way to go about trying to do that is to start out by mapping out all of your individual steps, like without worrying about the individual energies and things like that to start with. And I think that the best way to usually do that is to go ahead and start with your overall reaction. So we have that magnesium as a solid that's reacting with Br2 as a liquid, making our magnesium bromide as a solid. Right? Those should be kind of our individual, sorry, not our individuals, that's our overall reaction that hopefully all of those individual steps that are kind of outlined over there will actually kind of combine into or make. So how we go about doing that. The very first step that we should always be trying to get to, and something to kind of keep in mind, we kind of always want our initial phases of things to be in the gas phase. And so if we're not in the gas phase right away, that's the first thing that we actually want to do. And so in order to get to the gas phase, the first thing that we're going to end up doing here, for the magnesium or for our metal, it's usually pretty straightforward. The metals are always going to have pretty much the same first step. We're going to turn them into the gas phase by undergoing what we call sublimation. Right? And so we refer to this as our sublimation energy. So sublimation energy to get our metal to the gas phase. Now, for the nonmetals, most of the nonmetals probably will be gases in their standard state starting out. So things like Cl2 or F2 or things like that are in the gas phase already. But in this case, the bromine isn't. So in this case, we're going to get our Br2 to be in the gas phase. This is if we're going from liquid to a gas as a change, that's vaporization. And so there's going to be some sort of vaporization energy for this step. All right, now next, we're in the gas phase for both of them. For the magnesium, we're ready to go ahead and start ionizing because it's already an individual atom, but for the bromine, we're not. And so for the bromine, we're currently at Br2 as a gas. what we really want to get to is just plain bromine atoms in the gas phase. And in doing so, since we're breaking apart Br2, we're going to end up with 2 individual bromine atoms in the gas phase during that process. And that step we often think of as a bond dissociation step. And so you might see or be given bond dissociation energies for different diatomic compounds. For our magnesium over here now, I'm sorry, at this point, sorry, let me go back up one step. We now have both of our elements in the gas phase as individual atoms. Here, with the fact we have 2 individual atoms, that's fine. That's actually going to matter for the stoichiometry that we're about to see in a second anyway. Now we can go ahead and ionize things. So for the case of bromine, we have like basically one more step for it where we can get to Br minus. We're going to get 2 of them, right? Still in the gas phase. And going from Br neutral to Br minus, this is our electron affinity. So we refer to that step as the electron affinity step in this process. For our metal cation now, our magnesium, the one thing we want to pay attention to is you can only change your charge by basically 1 at a time. And when we see our steps actually written over here, we actually have 2 steps where the charges are changing because there's actually 2 ionization energies that are going to be going on here. So for magnesium to go from neutral magnesium to magnesium plus 1 in the gas phase, this would be what we call our first ionization energy. And I am going to abbreviate this with IE for ionization energy. And then we have a second ionization energy in order to get our magnesium 2+. So, and one thing I will point out, this is pretty much the maximum number of steps you will ever see in this cycle. You're never going to see there be more than this because we have a cation that needs multiple steps to get to its final charge, and we have a nonmetal that has to be vaporized and then broken up from a diatomic as kind of its initial steps. More often than not, you're probably only going to have a metal that might go up by 1 charge. A lot of your nonmetals start in the gas phase, so your first step might be bond dissociation and then the electron affinity. But the general thought process is the same. Get your atoms in the gas phase, or get your elements in the gas phase, get them to be individual atoms, then do your ionization steps. Once you have your ions with the right charges, now you can put them together as one final step, right? So we have our magnesium 2+ plus 2 bromide ions. All of these coming together are going to make our solid. This is our lattice energy step. Now, my purpose in kind of outlining all of this is that once we have all of our steps, we can be given problems that give us all these energies with the steps written like this, or we could be given problems where they actually give us the names that are going on in these different steps, which is also very common. Like they might tell you the sublimation energy of magnesium is this, or the bond dissociation energy of Br2 is this. And so those are things to just kind of keep in mind when you're looking at them. Now, to come back and look at our energies, I'm going to fix one little thing here. This Br2 should be subscripted, so I'm going to add that part here to kind of clean that up for a second. Sorry. And then for each of these energies, we just want to go through and figure out, all right, how does this all fit into the grand scheme of things? In terms of what we're looking for the energy change for the whole process. So I'm going to put a question mark under that arrow right here for the whole reaction. But if we notice, like the sublimation energy is magnesium solid going to magnesium as a gas. Well, magnesium solid going to magnesium as a gas is one of the steps we're given. It has an energy that's 147.1. Let's slide this over just a little so you can see them all, hopefully. So this is positive 147.1. And now the second step for the magnesium, going from magnesium gas to magnesium plus 1, that first ionization energy, notice we're given that as a step as well. And so here is that energy. And for all of the steps on your metal, they're all going to be positive values. Always expect them to all be positive for your metal. So 737.8 for the first ionization energy. And then the last one is for the second ionization energy, for the magnesium, last step for the magnesium is 1451. And all of these have units of kilojoules per mole. So that when we add everything up at the very end, we'll also then get kilojoules per mole for our reaction enthalpy of formation. All right, so there's our energies for each of those steps on the metal side of things. Now if we look at our metal, the vaporization energy, Br2 as a liquid to Br2 as a gas. Here, liquid to a gas, energy is 30.9 kilojoules per mole. And that is a positive value. Again, vaporizing something's always going to take energy to do. You have to add heat if you're trying to boil something. And then we have a bond dissociation energy as our next step. Bond dissociations are also always going to be positive because we have to add energy to break any bond. And so here we see Br2 going to 2Br, positive 224 kilojoules per mole. And now the next step is one that we actually want to be a little bit careful of, stoichiometry. So here we have a coefficient of a 2. For the way I have mapped this out, whenever we have a coefficient at the start of one of these steps, if you have an energy for just one of those things, then you have to be careful about that energy, right? Because notice over here we have Br as a gas plus an electron makes Br minus. The energy for that's negative 325 kilojoules per mole. But we have 2 bromines that are undergoing that change. So we actually have to take that negative 325 and double it, or multiply it by 2. So for that electron affinity, it's negative 325 kilojoules per mole. But we have to double that, right? So we're going to double that because there's 2 bromines undergoing that change. And now the lattice energy, this last step, they give us, magnesium 2 plus 2 Br minus going to MgBr2. For that step, they tell us it's negative 2,441 kilojoules per mole. And now if we want this overall energy, we should be able to just add up everything, all of our individual steps. And so I'm going to take a minute and actually kind of punch these numbers in as well, and give you a chance to do the same to kind of hopefully check the numbers here. But if we're adding all of this together, we have 147.1 plus 737.8 plus 1451 plus 30.9 plus 224 plus negative 325 times 2, or plus negative 650 if you just want to write it that way, plus then a negative 2441. And at the end of all of this, I get an answer. I'm going to scroll this up just a touch. I get negative 500.2 kilojoules per mole for that enthalpy of formation. Now, most enthalpies of formation for ionic compounds, the majority of them probably will be negative. Some will just be a little bit negative, some will be a lot negative, maybe like this one. Occasionally there might be one that's a positive value, although like I said, the majority of them usually will be negative. For all of the individual steps though, their signs are pretty much always the same. Like sublimation and all ionization energy is always positive. The vaporization, or really the bond dissociation energy, is the first step for most nonmetals. Those are always positive. Electron affinity, that's typically going to be negative for all of our nonmetals, as is the lattice energy for all of them. The lattice energy is going to be negative for all of these as well. And so kind of keep that in mind sign-wise for things. And the only other kind of like variations a lot of times, these problem types that we'll usually see is going to happen when we have, instead of looking for like the total energy, maybe we're looking for the energy of one of these steps. So maybe we're solving for the lattice energy. So they give us all of these energies and they give us a total, and we want just this one piece. We can still find that, right? Because the total has to be the sum of everything added together. So if I'm looking for just this one piece, that one piece should be my total minus all of the other steps, would be the setup for that. And the biggest thing to just be careful of as you're doing these Born-Haber cycles, just be careful about signs of things and be careful about the stoichiometry when it matters. If you have a coefficient in your balanced steps that you're doing, but the reaction you're given doesn't have coefficients in it, or if it gives you like a bond dissociation energy and it's units of like kilojoules per mole for Br2, if for instance it was 1/2 Br2 going to Br, or like the previous example in the slides that was 1/2 Cl2 going to Cl, you would have to multiply the bond dissociation energy by 1/2 because you only have a 1/2 mole making that change. So kind of pay attention to those stoichiometry parts because they do matter. Right here we saw the 2 bromines going to 2 Br minus. That's why we multiplied this electron affinity energy by 2. And so kind of pay attention to that, because 90% of probably all the mistakes I see on these Born-Haber cycle type problems has to do with the stoichiometry and just not tracking the stoichiometry properly for any steps that do have that there. All right, so that's it for this example. I'm going to kind of jump back to our slides here now. And if we go on and talk a little bit more about lattice energy, there's a couple of trends that we can actually start talking about as well. And the biggest thing is that lattice energy, in terms of what things have the biggest impact on the size of a lattice energy for different ionic compounds, because this is something that does actually come up frequently, both in 1211 and 1212 even, is kind of what are some approximations as far as like, general sizes of lattice energies between two different compounds, like being able to compare them and figure out which one's likely to have a bigger lattice energy. And so this is one way to look at calculating lattice energy. We are probably not going to use this equation for anything, at least not for my lectures. I don't plan on using this equation. But what I do care about from this equation is just things that will tell us about general trends. Out of this whole equation, the only things that aren't constants are Z plus, Z minus, and R. That's it. Z plus and Z minus are just the charges of your cation and anion respectively, and R is the combined ionic radii, or the size of your ions. And so turns out those are the two things that really matter the most to determining lattice energy, because like pi, epsilon naught, E, the capital A, all of these are just constants. And so those are not things that are going to have any impact on the lattice energy itself. So the biggest things I would point out from this, bigger charges are going to result in a much larger magnitude of the lattice energy, or a much more negative lattice energy. If we have smaller ions, that would also result in a greater magnitude, or just a more negative lattice energy. And so if you're trying to figure out, like, how do we get, another way to think about these lattice energies is the strength with which those ions are held together. And so really small ions with really big charges are going to be held together the tightest. The bigger our ions get, or the smaller the charges get, then the less tightly those things are going to be held together. It's a weaker attraction at that point. And so you will sometimes see problems kind of like asking you to compare lattice energies of things. So for instance, you might have a question that asks you, what's the lattice energy of NaCl compared to NaBr? Like which one is bigger or smaller? Now, you do not need to memorize any of these numbers in this table, like please don't. But this table is nice because it shows us, again, the trends. Right? So I was mentioning like the trend between sodium chloride and sodium bromide. So here I have sodium. If I want to pair it with chloride, this is the lattice energy. Now it's a positive value in this particular table, but it's 787. If I compare it with comparing the sodium with the bromide, now it's 747. It went down. Well, why did it go down? Well, bromine is a bigger ion than chlorine. Right? Bromine is right below chlorine on the periodic table. So since bromine is bigger, if we think about that equation we just had on the previous slide, R is bigger, so that means the lattice energy should be getting smaller. That's kind of the general trends that we see. And we see that all throughout this chart. As our ions get bigger as we go to the right or down, we see our lattice energy shrink because we have bigger ions. Now, there are some other factors, especially here as we go down. We see a big spike, but that's because it went from +1 cations to +2 cations. Right? +2 cations, the charge matters a lot. Big charges are going to cause our lattice energies to be much higher, is kind of generally what we will see. And so we see that here, like beryllium 2+, much bigger than like lithium, which is the element right next to it on the periodic table that's in group 1 instead. And likewise then size, as our ions get bigger, lattice energies get smaller. But again, ion charge matters. Here we go from I- to O2-. O2- is a pretty big anion because it has a -2 charge, but because it's a -2 charge, just the size of the charge makes all of these lattice energies much bigger now. And so that's kind of the general trends that we typically see in most of these. Bigger charges, bigger lattice energies, bigger sizes are going to lead to smaller lattice energies. And you're able to compare just kind of general trends with that information. All right, now, that's kind of the extent of what we'll often focus on for the ionic bonding portion of this chapter. What I want to do, though, is to at least start a little bit to talk about covalent bonding. And then leave our next lecture for actually talking about what we call Lewis dot structures and looking at structures for covalent compounds, because that's going to be a major focal point. You'll see it a little bit in lab already this week, but that'll be a major focal point kind of for the rest of this semester, and really a lot in 12-12, and for anyone going on to organic, you'll see it pop up a lot there as well, because most of the focus of the things we're going to be doing in general chemistry, and particularly for organic, and especially, are often going to be covalent in nature. And so we want to understand what's going on with their bonding. But for now, I just want to talk about kind of some general trends and patterns. We were just looking at all of those lattice energies a second ago. I want to kind of compare, at least loosely, this isn't a great direct comparison, but I want to compare some to what we call bond dissociation energies for breaking covalent bonds. And so when we have covalent bonds, here we see a bunch of different energies for covalent bonds and what it would take to break these bonds. That's what these bond dissociation energies are. It's the energy for breaking the bond that's being listed there. So for instance, if we have a standard just carbon-hydrogen bond, it takes on average about 410 kilojoules per mole of energy to break those bonds. If we have something that's like an oxygen-chlorine bond, that's much weaker. It only takes like 200 kilojoules per mole. But notice all of these numbers are much smaller than the lattice energies we saw on that last slide. And again, this isn't the best direct comparison for like strength of ionic versus covalent bonding, but again, when we see the properties and stuff we're going to talk about in just a second, it kind of furthers this idea though that ionic bonding in general is usually stronger than covalent bonding in terms of just like the actual energies that are often involved. Now, I will point out one thing here for covalent compounds, and again, don't worry about memorizing any of these values. There's fewer general trends here for us to even talk about at this point in time. Maybe at the end of 12-12, when you've had a lot more kind of general chemistry, we could come back here and make more sense of why some of these bond energy trends might be what they are. But for right now, the biggest thing I would really point out is just that up here we have all single bonds, down here we have some double or triple bonds. The more bonds between atoms, the stronger those bonds get, so the higher the bond association energy values get as a result. Right here we see an oxygen-oxygen single bond of 180, oxygen-oxygen double bond is 498. So in some cases, a double bond is more than twice as strong. And so that's important because there will be some applications of using these bond association energies to calculate enthalpy changes for reactions, kind of coming up at the end of this chapter. And to be able to do that, we do need to know more about the structures of the compounds to know, do we have double bonds or single bonds that are being broken? And we haven't done anything yet this semester to talk about how to know that information. And so those are going to be the things that we're going to be getting into a lot of detail on in our next lecture. All right. So comparing just real quick, kind of still sticking to comparing ionic and covalent compounds, some different things to kind of keep in mind. So here we're comparing sodium chloride to hydrogen chloride, HCl. And notice it is hydrogen chloride if I'm talking about the compound, not in the aqueous phase. Because if it's in the aqueous phase, HCl is then hydrochloric acid. So that's why I'm calling it hydrogen chloride. Here, if it's just the compound, that is different. And so comparing general properties of these two different compounds, their molar mass is a little bit different. The sodium chloride is a little bit heavier. But the biggest thing is just physical appearance, physical properties. Sodium chloride is a solid because it's ionic. HCl is actually a gas if it's not dissolved in water, and it has a covalent bond that's holding it together. And notice the big thing here I want to show, melting point and boiling points, which kind of go with these physical appearances. Melting points and boiling points for our ionic compounds are usually really, really high. And if you think about it, how many ionic compounds that you know of are not a solid? Probably not very many, or maybe none. There's not that many ionic compounds that are not a solid. Almost all of them are solids. That's because they usually have really high melting and boiling points. If you talk about covalent compounds, especially small covalent compounds, most of them are gases. Maybe sometimes liquid if they start to get a little bit bigger or have really strong what we call intermolecular forces that we'll talk about in 12-12. But for the most part, most of our covalent compounds, if they're tiny, are usually gases, which is very different here than what we're seeing for our ionic compounds. And again, a lot of that goes back to the actual kind of attractive forces between these things. And again, there's a little bit more to it than kind of what we've seen, and we'll see the kind of rest of that picture when we get to 12-12. But that is something I just want to kind of reemphasize. Like ionic bonding in general, usually something that's stronger than covalent bonding. And we can see properties that kind of back that up. All right, now, as a general introduction to covalent bonding, just to get kind of a visual depiction of kind of what's going on and how electrons are shared, and some other things that will actually impact how electrons are shared. We'll take a look at kind of in a similar fashion to what we did with ionic bonding, going a little bit more in depth. So for covalent bonding, our electrons are shared. So we just said instead of being transferred. But one of the things that we want to kind of keep in mind is if electrons are being shared, doesn't always mean they're going to be shared evenly. And we'll have something here in a second that we'll look at that will help us figure out when that might happen. We normally see our covalent bonds or electrons being shared when we have a bond between two nonmetals. And again, this goes back to kind of our periodic trends and the fact that we said that we have two elements that both want electrons and don't want to give them up. And so the net result is that we end up with things that share those electrons instead. And if we think about visually too, making a covalent bond, you typically get attractions between the positive nucleus of one atom and the general electrons or electron cloud of the other. And then you also have repulsions, though, between the electrons on each, or the nuclei on each, probably less so, unless we get them really, really close together. But you basically have this balancing of attractive and repulsive forces. And so the result of that, if you're trying to kind of balance all of that out, is that covalent bonds always have kind of this sweet spot in terms of how close two atoms want to get to one another to make that covalent bond. And so most covalent bonds will have a bond length that's associated with them. And another way to think about bond lengths in general, and kind of a good general trend, the stronger your bonds are, usually the shorter the bonds will also be. Now, the size of the atoms also matters to that, so it's not a hard, fast rule that applies to everything, but in general, the shorter your bonds get, usually the stronger they get as well. It's something else to kind of just keep in mind. And we'll see that's something else that'll come up more here this semester as we talk more with structures of compounds. Oops. And so the last thing here, I apologize, that slide is actually in there twice. The last thing here that I'm going to mention, we mentioned electronegativity at the end of the previous lecture. We're going to see it kind of show up here again as we talk about covalent bonds, right? And to kind of refresh ourselves, electronegativity, it's the ability of two electrons to pull themselves, the ability of an atom to pull electrons towards itself in a covalent bond. And the periodic trend that we said before was that it increases up to the right. And in fact, the reasoning behind that, again, same as what we saw before, it's the higher effective nuclear charge. This matters, though, for covalent bonding, particularly for what I was saying about how electrons aren't always shared evenly, right? These numerical numbers that we're seeing down here, these in this chart, these represent basically how badly something wants electrons. And we see fluorine has the biggest value of any of these elements. Fluorine, that means, is the most electronegative element. It wants electrons the most. So if fluorine makes a covalent bond to some other nonmetal, like nitrogen or sulfur, since fluorine's electronegativity is so much bigger, that means fluorine's still going to pull most of the electrons towards itself. You're not going to end up with a full ionic interaction, but you are going to end up with something that's not really a even sharing of those electrons. And we do have some terms to help kind of describe what that represents. And so when we talk about bonding, we can actually go more in depth than just covalent and ionic. And we can actually take covalent and break it down into two different versions. We can have nonpolar covalent, and really that means our electrons are evenly shared. There's no partial charges on anything. This happens if the difference in electronegativity between the atoms making their bond is less than 0.4 on that chart from the previous slide. And you'll never have to remember the charts in that previous slide. If we need those values for anything like this, we will provide those electronegativity values. But one thing I would keep in mind for nonpolar covalent bonds, the most common examples of this you're going to see are an element bound to itself, like an O2 or H2, or a carbon-hydrogen bond. Carbon-hydrogen bonds are right at this kind of 0.4 cutoff, and we consider those bonds to be nonpolar. And that's really kind of actually one of the big foundations of organic chemistry, is the fact that carbon-hydrogen bonds are fairly nonpolar. They share their electrons very evenly. Now, if we have two elements that will still share their electrons but don't share them evenly, we get what's called a polar covalent bond. And we call it polar because there are going to be some partial charges that form, like a partial positive or a partial negative charge. Whichever element's more electronegative will have the partial negative charge. The less electronegative element will have a partial positive charge instead. And this happens if that electronegativity difference between the two elements we're looking at is between 0.4 and 2. Now, this is not like a hard, fast, 100% always true rule. We can have some compounds that actually are ionic, even though their electronegativity differences may be in this kind of range. That can happen. But for the most part, this is kind of the general rules that we normally look at. And then ionic compounds are kind of one step further. If our electronegativity difference is really, really big, if it's bigger than 2, now this is when one element wants electrons so much more than the other that it basically just rips those electrons off, and then we get ions, and now we have ionic bonding instead of a type of covalent bonding. And so that's how electronegativity can often be used to kind of view and kind of further describe the bonding that's occurring. And just again, to visually kind of show the difference between like nonpolar covalent and polar covalent and some different visual representations. This top example would be here, this is Cl2, chlorine being bound to itself. Everything here is fairly green and yellow in color, which is a neutral color in this kind of electron cloud picture that's being shown here. For hydrogen being bound to chlorine, chlorine's much more electronegative. If I went back to that chart, the chlorine I think is 3.5, whereas hydrogen's 2.1. So that'd be like a difference of 1.4, which on that previous slide would have fit pretty much right in the middle of that polar to covalent range. So hydrogen-chlorine bond, it is going to make a polar bond. Chlorine's more electronegative. That's why it has this partial negative sign. That's what that little delta symbol means. It's partially negative, partially positive on the hydrogen because it's less electronegative. And visually, the partial negative charges are usually going to show up as kind of red in a lot of these kind of electron cloud images like this that you're seeing, whereas the blue color usually represents a positive partial charge in those images. And so there are these different types of covalent bonding. We probably won't do a ton with looking at this semester. We will talk about kind of in the next lecture, actually might be a couple lectures from now still, about how to figure out if a molecule is polar or not in a little bit more detail. For now, we can expect to figure out if a single bond is polar just based on those electronegativities. But we'll look at kind of how whether or not whole molecules are polar a little bit later on this semester. And when we get to 1212, then we'll spend a lot of time really caring about whether molecules are polar or nonpolar, because that's going to dictate a lot about their properties. And so that's kind of where we're working towards. But it also means that a lot of the stuff that we're doing right now, especially the stuff we're about to start with Lewis structures and a couple things that come after that, are going to be really, really important because they're really crucial to the next class in the sequence, 1212. And if you go beyond 1212 to organic, they're still really crucial to those courses as well. And so this stuff is some of the more important stuff this semester because of how much more it will show up down the road. And so if you have questions as we kind of get, especially like I said, on the Lewis structure stuff we're about to start, please don't hesitate to ask. But as far as today's lecture, that's where I'm going to kind of cut things off. It gets us something set up so that next time what we'll talk about for our covalent compounds is the structures of things and how we figure out what structures of covalent molecules are going to look like and go about drawing what we call these Lewis dot structures.